Good morning. Today I'll be taking you through calibrating linear sensors for robotic system, ensuring precision performance. Lesson goals and objectives. By the end of this session, you will be equipped to first identify sensors, which is experiment with varying linear sensors like light, color, ultrasound, ultrasonic, and then temperature sensors. Second, apply mathematics. Use straight line linear equation like y equals mx plus c to interpret raw data output from devices. Calibrate and scale. Calibrate sensor hardware to map raw electrical data into precise real-world maximum and minimum ranges. Making robots aware. How do robots look, feel, and think? Imagine an autonomous robot vacuum cleaner traveling around a modern home in Ghana. How does it manage to perfectly clean rooms without breaking furniture? Senses. Senses it acts as the robot's eyes or feelers to gather environment data. Actuators. It acts as the muscles, which is the motors or wheels, to react and turn around safely. So, what are linear sensors? When we talk of linear sensor, it produces an output signal that changes proportionally relative to physical quantity being measured. Light sensors. When we talk of light sensors, output values shift up and down depending on detected light intensity. Ultrasonic sensors. It measures physical distance by tracking sound wave reflection times. When we talk of the temperature sensors, voltage changes directly based on environmental thermal conditions. The problem of the raw source, the problem of the raw sensor data. Microcontrollers like Arduino or Raspberry Pi reads sensors outputs as raw analog voltage values. Example, numbers ranging between 0 and 1023. These raw numbers don't explicitly signify anything useful to human users or control code until parsed. When we talk of raw value, we have 820, which is uh, which talks about what the actual lacks. Then the second raw value is 102, which talks about what is the distance in centimeter. So calibrating bridges this exact gap between mapping system signals directly into human readable raw world values. Mathematical foundation, which is the y equals ms plus c. Because these relationships are perfectly proportional, we use the equation of a straight line to analyze system data values, which is the y equals ms plus c. So the c is calibrated output, or the real world metrics like loss or temperature. X is the raw data input reading from the hardware. The M, it means the slope or scaling multipliers step factor. When we talk of the C, the y-intercept, which is the offset adjust point. So the diagram here, it shows the minimum point from the minimum point up to the maximum point of the raw input. So by walking through calibrating a light sensor, our first scenario is that a sensor registers a raw value of 100 in complete dark, which is the zero lux, and then 900 in intense bright condition, which is the 1000 lux. So step one is to calculate the slope, which is the m. So when you talk of the m, we have we have m equals y2 minus y1, all divided by s2 minus x1. So m is equal to 1000 minus 0, all divided by 900 minus 100. So our m will give us 1000 all divided by 800 minus, which is equal to 1.25. So our step 2 is that you solve for the intercept, which is the c. So the formula is y equals ms plus c, which uses the point 100 and 0. So 0 is the y. So 0 is equal to 1.25 multiplied by 100 plus the c, which is the intercept that we are about to find. So 0 is equal to 125 plus c, which is c is equal to minus 125. So final calibrated formula is actual x equals 1.25 times the raw readings minus 125. So calibration reference mapping. The sensor types. We have light sensor, ultrasonic sensor, and then the temperature sensor. When we talk of the light sensor, its raw range is the X, which is the light sensor has 100 to 900 range, raw range, and then its target real range, which is the Y, is 0 to 1000 lux. Then its calculated linear mapping function is y equals 1.25x minus 125. When we talk of the ultrasonic sensor, the raw range is 40 to 400 real range. So its target real range is 10 centimeters to 100 centimeters. And then its calculated linear mapping function is y equals 0.25x minus 0. So the temperature sensor is also, its raw range is 200 to 600. Then its target real range is 0 degrees Celsius to 100 degrees Celsius. And then its calculated linear mapping function is y equals 0.25x minus 50. So note here, these linear functions allow immediate runtime code conventions within any robotic microcontroller operating system. So you go to the real world robotic application, which is the automated display adjustment. So once calibrated, systems can accurately, accurately perform high-level conditional logic loop operation flawlessly. So if lux is less than 200, then we should increase our screen brightness. Else, we should set standard brightness, then we will end. So without calibration calculations, the operating system software couldn't safely discern standard classroom illumination profile from pure night settings. So to check your understanding, level 1, which is the recall, what is a linear sensor? I'll be waiting for your response. So what is linear sensor? Give any two examples. Our second question is that explain the key differences between real sensor data output and calibrated metrics. Question 3 is that how do you construct a line formula if given two separate coordinate points? Okay, so the fourth one, outline an experimental workspace layout configuration designed to calibrate and run ambient room systems. So this is the end of the lesson. So our summary is that calibration performs arbitral electrical electronic real signal into meaningful real-world physics values via the linear and engine properties of y equals ms plus c. So this is a take-home assignment. We'll complete the calibration worksheet questions on the scaling temperature sensors. Thank you very much, Bill Mate.